Hi everyone, I'm here with Smash to introduce you to thermochemistry. Okay, so before we bring in Smash here, put him over there. Okay, let's talk a little bit about different forms of energy and their interconversion, and that really plays out in the topic of thermochemistry in Chemistry 101. Okay, now if you remember at the very start of the semester I asked for a definition of what chemistry was. It was a study of matter primarily, right, and the energy associated with the changes of matter. So now we're going to get into the energy changes we see when a reactant turns into a product, essentially. Okay, now to get a handle on this, the best way to do it is with an everyday analogy with Smash here, right? Okay, so think about this. So everyday physical objects, a golf ball, a tennis ball, something, right? Okay, so think of a golf ball or a tennis ball flying through the air, right? And now when that ball's flying through the air, okay, it has two, in physics at least, two kind of simple forms of energy, right? Remember what they are? Well, it has kinetic energy, right? So that's, you know, the kinetic energy is the energy of movement, right? So you may know the equation, half mv squared. So the faster it moves or the bigger it is, the more energy it has. So think of catching a medicine ball back in high school in gym class, right? It didn't move so fast, but it was really heavy, so that was a lot of kinetic energy it had, right? But if you catch a ping pong ball moving at 100 miles an hour, you don't feel it, right? Because it doesn't have much mass. So, you know, half mv squared is kinetic energy. So obviously kinetic energy scales with velocity squared and mass. Okay, so if velocity goes up a little bit, kinetic energy goes up a lot. Okay, squared term. Okay, now so that's the energy of movement, if you like, hence the word kinetic. Okay, now the other one is a little bit harder, right? Okay, if I take a book and I put it on a high shelf, okay, I've lifted it through a distance under gravity, right? The Earth's pulling it down and I'm pulling it against the Earth, right? So I'm actually storing energy in the book, and if I put it on the shelf and it topples and falls, it'll fall back down again, right? So it's actually stored energy. That's potential energy. Okay, so potential energy. Now, potential energy is pretty simple. You take a mass and you take it under gravity at a certain height. So you lift something up, mgh, right? Okay, so I can take Smash here, I can lift him up, and I've stored a little bit of energy in him, yeah? If I let him go, he speeds up, hits the table, he turns his potential into his kinetic energy, okay? And his kinetic energy is maximized right when he hits the table. His potential energy is maximized right at the highest point here. And there's an interconversion. So energy can be changed from one form to another. Now, if this was class, I'd have a special kind of little fish puppet I have, which is at school, right? But, so, stunt bird demo, all right? So, I'll use the fish symbol though, so it's easy to draw. So if I take my fish, right, and, you know, energy scale, right? So I lift the mass, I lift the fish up to a high point, right? Okay, or the penguin in this case, and then drop it down. Yeah, drop. The fish gets kind of squished, right? And it turns its max potential energy into, right before it hits max kinetic energy. It's moving as fast as it possibly can right at the point where it hits the ground, right? Okay, fair enough. Now it's kind of interesting that, you know, when our friend Smash here hits the ground, oh, you can actually, you heard a sound, right? So maximum potential turns into maximum kinetic, and then that kinetic, once he hits the ground, he's not moving anymore, right? So he turns it into other energy, sound we heard, and also heat. It turns out that essentially all energy ends up as heat in some way, shape or form, okay? In fact, if you went to Niagara Falls and you measured the temperature of the water above Niagara Falls, just about when it falls over, and then right at the bottom, it's about half a degree hotter at the bottom because it's turned that potential and the kinetic into heat. Okay, so that's kind of interesting. All right, now we see a similar thing in chemistry, right? So we have reactants, yeah, which are like the fish, you know, high off the ground. And then when we turn them into products, energy comes out, right? Okay, so we turn essentially stored chemical potential energy called enthalpy, right? So we can do a symbol, enthalpy. Okay, so stored chemical potential energy, which is basically stored in bonds, right? Okay, the stronger the bond, the more energy is stored in it, right? Okay, so the energy stored in the bonds of the reactants, okay, is different than the energy stored in the bonds of the products. Okay, so reactants turns to products, and that difference in stored energy comes out as heat. That essentially, in simple terms, is the first law of thermodynamics. We'll expand on this in a second, but reactants have stored energy. Products also have some stored energy, but less. From turning from reactants to products, i.e. a chemical reaction, heat comes out 99% of the time. Okay, all right. All right, so now, heat comes out, and sometimes if we produce a gas, it can maybe push a piston, right? So that's called pressure volume work. Most chemical reactions don't produce a gas, so that's normally not the case. We'll see it in more detail in a second. All right, so when energy is transferred or converted to another form, it must eventually appear as heat and or work. In chemistry, mostly heat. All right, so the simple fact now, thermochemistry can be confusing because the concepts, right? But if you get the concepts, it's actually pretty straightforward, all right? So that word enthalpy. Enthalpy is a special chemistry word. It has the symbol H, right? So the potential energy inside elements and compounds is stored within their bonds, okay? So think about a bond a bit like a stick, yeah? It costs energy to break it, right? So there must be kind of energy stored in there, if that makes sense, okay? So breaking chemical bond requires energy, right? Okay, you heat something up hot enough, you'll turn it into atoms eventually, yeah, several thousand degrees C, right? Because you snap all the bonds, right? You provide enough energy to snap all those twigs, right? So if breaking a bond requires energy or heat, making a bond gives you heat back, okay? And that's where heat comes from in chemical reactions. I break all the bonds in the reactants, fair enough, that costs some energy, right? And then I make all the bonds in the products, and that typically will be stronger bonds because nature loves stable, and that difference in energy between the two reactants and products, in terms of their stored bond energies, their enthalpies, delta H we call it, comes out as heat. Okay, now, if you look in a physics book, the first law of thermodynamics is more explicit, right? So it says the energy change for maybe a chemical system equals Q, which is the heat. Q, if you remember from your food lab, is the universal symbol for heat energy, right? Plus W, which is work. So if I lift up a book, I've done mechanical work. If I am a gas and I push back a piston, that's mechanical work. So that only applies to gases, all right? That's PV work, right? Now, so here are the things. So there's energy transferred from reactants to products. The energy change, the heat that comes out or goes in, the energy total, and then the work, okay? So the energy change from reactants to products is a combination of heat and work, okay? So for chemical systems, as we mentioned, usually we don't make gases, so it simplifies. We don't use E in chemistry, we use H. So the stored potential energy comes out as heat. Okay, that's the first law of thermodynamics. Now, what does that mean? When we do this is the first law of thermodynamics, right? This is all about direction. So loss of energy going from reactants to products. So if you think about the fish on the shelf, right, or the book on the shelf, has lots of potential energy, right? And then you drop it, the potential goes away and turns into kinetic, yeah? So I have energy stored in bonds, yeah, enthalpy, and then when I turn reactants to products, the stored enthalpy changes, it's delta H. But I lose energy, right? I lose energy, therefore what's lost by the system comes out as heat, okay? So it has to be careful with the sign conventions. What's lost going from reactants to products, I lose heat, it comes out as heat. Or I lose energy, it comes out as heat. Okay, that's the first law of thermodynamics in a nutshell. Minus delta H equals plus Q. Okay, super important equation. Okay, simple, but super important. As long as you understand the sign conventions, the loss in words, the loss of stored chemical potential energy as a change from reactants to products equals the heat that comes out. That's it. Okay. Now, let's get a few definitions down before we continue. All right. So, maybe you've heard of these words, exo and endothermic, okay? I often talk about complementary learning, which is if you learn one, you don't have to do the other because it's the opposite, right? So I like exothermic, okay? Exo reminds me of exit, okay? So exothermic reactions, heat comes out, right? If heat comes out, Q is plus, all right? So that's 99% of all reactions. If it just happens to be the other way, heat goes in, right? Q is minus, delta H would be plus, we just change the signs. That's an endothermic process, all right? So, a few important definitions. Thermochemistry, chemistry with heat, right? So we're just going to essentially add a number for heat on the end of an equation. It will tell you, hey, how much heat went in or out for that process. That's thermochemistry. So we do these balanced thermochemical equations. They're just like regular equations. We just add on the back the number of kilojoules usually that went in or out with a sign. So we put delta H equals on the back, okay? Thermodynamics is a broader study of this thing. So thermodynamics, heat movement. So we look at heat transfer into and out of systems. For an engineer, thermodynamics is a big deal, right? Okay, so the efficiency of engines and things like that is very thermodynamic, all right? So the flow of energy in and out of places, systems we call them, that's the study of thermodynamics. Now heat, you got to be careful with heat, right? Okay, if I can dig up, maybe I'll put it over there if I can find it. If I can dig up a picture of a Newton's cradle kind of working, okay, that kind of tells you what heat actually is, okay? So heat's kind of interesting. Let me draw you a little picture. All right, so maybe I'll draw it on the side so it's in the notes here. Did you ever wonder how a thermometer works? So here's a little container of water, say, right? And I'm going to stick my thermometer in there, right? There's my thermometer, there's my mercury, and there's the mercury tube, and there's a certain level, okay. It's all about what's happening in here, okay? So I have this glass barrier, and we'll just kind of zoom in, right? So that's the glass barrier, yeah, okay. And then on the outside, over here, we have a water molecule. And on the inside, we have a mercury atom. Yeah. If you've ever played pool, this makes absolute sense. Did you ever do a trick shot at a plant in pool, right? Okay. So imagine this water molecule, actually just put it here, all right? Not there. Okay. So this mercury comes in with a certain speed, hits this one, hits this one, hits this one, hits this one, and that one then acquires the same energy it had and flies off, okay? So it was a lower energy before, and through this kind of coupled collision, it flies off with the same energy as this. So heat transfer is really making molecules have the same energy. If they're the same mass, they have the same speed, right? Okay? So think of the water molecule and the mercury atom in this kind of collision across the barrier here. Now they have the same energy, they have the same speed essentially, right? So they have the same temperature, all right? So temperature is related to the speed, and we talked about that concept before, of a molecule, yeah? So molecules that are moving fast have a high temperature. Molecules that are moving slow have a low temperature. Molecules that are stationary have 0 Kelvin, no temperature, all right? Okay, so heat is the energy that flows in and out of a system because of a difference in temperature, right? Okay, so temperature, as we saw in our previous lab, and we'll get to that equation again, temperature and energy are related, they're proportional, but they're not equal, right? So when heat moves from one place to another, the place it goes to, the temperature goes up, right? Where it leaves, it gets cold, okay? So we can equate temperature changes with energy flow, right? And we typically measure, as we saw in that food lab, we typically measure temperature changes and then do the math to find heat, Q, right? We use that equation again shortly. All right, so between the system and its surroundings, all right? Now, I'll actually hopefully be able to find you a nice slide of a thermodynamic system, but very basically, a coffee cup is a thermodynamic system, okay? So there's some stuff in this cup, yeah? And that's where the action is going on, right? So maybe we've got a test tube with a reaction going on, we've got a cup of coffee, something, it's hot, it's made some heat, right? It's got heat. That will eventually leak out, right? So where the heat is the system. Where the heat goes is the surroundings, okay? So if I want to talk in broader terms, the universe as a whole is the surroundings, yeah? So you have a chemical reaction, the local system is what's in the test tube, right? So some chemicals are mixing in a test tube, they're reacting, making heat. It heats up the solution in the test tube. That is the chemical system. But there's no such thing as a perfect insulator, right? So that heat will eventually leak out, okay, by mechanisms like this, and heat up the surroundings. So the universe gets a tiny little bit hotter on average every time we do a chemical reaction, because heat eventually transfers from the system to the surroundings. So anything within the vicinity of the system is generally surroundings, but you know, in theory it's the universe. Okay, so you know, some jargony stuff there. Well, let's work with it and see where it goes. Okay, so first things first, some nice easy examples. Here's an example of your first balanced thermochemical equation. So recall that all chemical reactions either release heat, exothermic, heat out, exothermic, all right, or absorb heat, endothermic, okay, when they turn from reactants to products, all right. Now remember the first law of thermodynamics. Delta H minus equals plus Q. Plus means heat out, so that's exothermic. When Q is plus, delta H is minus, and it's exothermic. That's 99% of all reactions. Now, you may ask yourself a question, why are 99% of all reactions exothermic? Think about when you burn something, right? Heat comes out, doesn't it, right? That's because nature likes stable. It turns out that when you turn things with weak bonds into things with strong bonds, the difference in stored energy comes out as heat. Nature likes to make things with more stable bonds. Nature loves stable. Nature will turn unstable reactants into more stable products 99% of the time. So 99% of the time, these products here have stronger bonds than the reactants here, right? And we know that because heat came out, all right? Burning, heat comes out, yeah? Now if heat comes out, Q is plus, so delta H is minus. So if we see a delta H minus here, that's absolutely an exothermic reaction. So 99% of the time you'll have a negative delta H. There was a change, a loss of stored potential energy, which went to the surroundings, exothermic, okay? Now, there's a weird sign convention which I won't get into, right? Just take it kind of as given that, hey, when delta H is minus, it's exothermic and the products have stronger bonds than the reactants. Okay. All right, now, it is molar, right? Meaning that I have a 1 there, right? 1 mole of methane reacts with 2 moles of oxygen to make 1 mole of CO2 and 2 moles of water, right? When I do that reaction with those actual number of moles, that many kilojoules comes out as heat. All right, or delta H is changed by that, right? So we always use kilojoules, it's more convenient, and that is 890.3 for 1 mole of this reacting with 2 of these to make 1 of those and 2 of those, okay? So it's a bit like, this is called an extensive property. It depends, it does depend on the amount, right? So if I throw 1 log on the fire, it burns at maybe 600 degrees C. If I burn 2 logs on the fire, it burns at the same 600 degrees C. Wood burns at a certain temperature. It doesn't matter how much wood I got on fire, right? That's called intensive, right? Doesn't care how much. But energy is extensive. 2 logs burns twice as long as 1 log because 2 logs contain twice as much energy, right? We're talking about the energy here, yeah? So it doesn't matter if I have 1,000,000 moles of CH4, it all burns at the same temperature compared to 1, say, right? It doesn't matter how much I got. However, if I've got 2 logs on the fire, twice as much energy as 1. So if I had 1 mole of CH4, right, 890. If I had 2 moles of CH4 with excess oxygen, it's going to be twice as much, right, because it's twice as much. So we'll just do a simple thing. 2, and this is usually in kilojoules per mole, I should write that. 2 moles CH4 times 1 mole of CH4 is minus 890.3 kilojoules equals minus 780. Oh, so I got the number here, 80.6 kilojoules. All right. Now, careful. I made the classic error there, right? 2 moles of CH4 were combusted with excess oxygen. How much heat? That would be the enthalpy change, delta H. But if I want heat, I'm going to do that. Signs are very, very important. It said heat, which is Q, right? So in an exothermic process, it's plus, okay? Obviously 4, you can do the math, it's going to be twice that. What's that? Plus 35, 61.2 kilojoules. All right. Now, that's all well and good. We know a little bit about bonds as well, right? So maybe I'll show you on a separate piece of paper. All right, I'll include this in your notes. Okay, if you look in the back of the packet, you can get a reasonable approximation for enthalpies just from bond strengths, right? So if I'm burning CH4, right? So CH4, I give you that one letter. So 1 CH4, right? We'll do Lewis structures later, so you know how to do these. You know, we'll meet this in class later formally, right? 1 CH4 plus 2 oxygens. So I'm going to have 2 oxygens. Now, oxygen has a double bond. We're going to have that later, right? Turns into CO2. These bonds between oxygen and carbon are super strong, right? Okay, 1 CO2 and 2 waters. Okay, now what I want you to do to prove it to yourself that we can get a reasonable approximation, remember what I said, you break the bonds here and you make them over here. So the difference in energy stored in these bonds will be delta H, right? You get the numbers from here. Now these are average numbers, okay? These are average numbers, so they'll be close but not perfect, okay? So for example, in 1 molecule of CH4, I've got 4 single CH bonds. Well, there's C and there's H, right? So, oh, you find it? CH, there it is. 414, right? It's like a train timetable. So I've got 4 times 4, 1, 4. Okay, now I've got plus over here. This is on the reactant side, right? Now it's a double bond, got to be careful. 498, 2 times 498. Okay, let's work that out. Actually, I'll leave it to you guys, right? Let's work it out, find that value there, right? Now that turns into, this one molecule has 2 double bond COs, right? AO3, 2 times AO3 plus 1, 2, 3, 4, 4 times the OH, which is 6, oh, move that down, 464. Okay. Actually, why don't I do it just because, right? Actually, I don't have my calculator, so I'll let you guys do it. Okay, so work out these 2 values, subtract, and you know, there may be a sign difference for reasons we'll talk about later, but it's going to be the same order of magnitude as the answer we just got, okay? Which was 890.3, okay. All right, now remember the basic concept. Enthalpy is extensive, so 2 moles gives me twice as much energy, 4 moles, 4 times as much energy, 1 mole, right? Okay, so 2 logs on the fire gives me twice as much energy as 1 log on the fire, right? But wood burns at the same temperature, it doesn't matter how many logs I got. So temperature is intensive, doesn't matter on amount. Enthalpy is extensive, does depend on amount, okay. Now, hopefully, you're at the spot where you can answer this question in your own words, okay? So hopefully I've brought you along on this journey so far where we've discussed this weird concept of enthalpy, right? Okay, give you a moment, try and answer this question. What does delta H really mean in terms of what's going on with the reactants and products in the chemical reaction? If you can summarize in a sentence or two what delta H is after our just 20 minutes discussion so far, hey, let me know, right? Okay, if you got it, fantastic. This is what I wrote. H, which is chemical potential energy, which is called enthalpy, is stored in bonds. Okay, so every molecule has bonds, right? Every compound has bonds. Every element has bonds, right? Bigger scale things, okay? So there's a force holding atoms together, right? Okay, it's potential energy, it's holding them together, right? Okay, so therefore, delta H is the change in stored energy, chemical potential energy, I'll put that, when reactants turn into products. Very simply, I break all the bonds in the reactants. This is what happens in a candle flame, for example, right? So it costs a little bit of energy to break all those bonds, right? And then I reform stronger bonds. The bonds in one are stronger than in the other. There's a difference in stored energy. That difference comes out as heat. Okay, so hopefully that makes sense. If you've got that concept, first order thermodynamics, not so bad. All right. So let's just summarize that. So the change in enthalpy, delta H, is simply a measure of how much chemical potential energy has either been lost or gained when converting reactants to products. Okay, so the energy stored in the reactants and energy stored in the products is different. The change is delta H. Final minus initial only. So products is always the final place you go, right? And reactants is like the initial. So whenever you do a change, final minus initial. If you did a temperature, hey, you got to 20 from 10, it's a plus 10 difference, which is 20 minus 10, right? So final minus initial is delta H. Delta H, sign minus, equals plus Q. Okay, that's the first law of thermodynamics. So they're exactly the same value. You just swap the sign, right? So in a calorimetry experiment, which we'll talk about next, okay, we can find Q, because we saw that before with the food experiment. We can find Q experimentally, just change the sign. We can find delta H for the process, which is kind of neat. All right, so kind of mentioned that there. We can find Q experimentally, and you'll do another kind of virtual lab about that soon. Okay, but the food lab was very similar. So actually, when you do this next lab, always kind of think about the similarities with the food lab, because it does carry over kind of kind of similarly with the math, right? Which we'll talk about in a moment. Okay, so I'm approaching my time. All right, so that's an introduction. I'll keep going, all right, but I gotta kind of start and restart, if that makes sense. So I'll see you in a minute. All right, so calorimetry is kind of the experimental arm of thermodynamics. Okay, we've already done a calorimetry experiment, so it might be a good place if you're kind of want to catch up a little bit. Just go back to that pre-lab for the energy in foods, okay, and just look at how we talked about this equation right here. I'll just summarize it real quick, right? So in our experiment with the food, we had basically a container of water, right? Okay, then we had some kind of food underneath, right? Okay, so that was a peanut or something, yeah? So we set the peanut on fire, and what happened was the energy stored in the peanut was lost, so minus Q, and where did it go? It went into the water, plus Q, yeah? And we had a temperature probe in there, and we measured the temperature, right? Now, the energy that went in there is proportional to the temperature change, but it's not equal, right? Do you remember why? We talked about exchange rates, right? So depends on what this stuff is, yeah? There's an old phrase, and it's called a watched pot never boils, right? What that really means in chemistry, and we'll talk about it when we look at the numbers in a second in more detail, is that the exchange rate's that terrible. So the exchange rate between water and temperature, or water and energy, I should say, is not great. So it takes a lot of energy, 4.184 joules, it turns out, which is a big number in this science, okay? It takes 4.184 joules to raise 1 gram of water by 1 degree C. So watch pot never boils because it's got a super high heat capacity. It's got a really poor exchange rate, okay? So we have to factor that in, and then also the mass of the water. The more water that's in the pot, the longer it takes to boil, right? The more energy you've got to put into it, right? And then finally temperature, multiply those two things. So that's my exchange rate, mass of my water, temperature change of water. Hopefully you remember that from the experiment, okay? So the heat that went in there is the exchange rate times the mass times the temperature. Exchange rate is joules per gram per degree C, mass is in grams, temperature change is degrees C. So yeah, joules equals joules. All right. Okay, so hopefully you remember that from before. Now, the difference between the food experiment and future experiments is that in the food experiment we kind of brought in heat from the outside, yeah? However, if I just have a cup, right, and I throw 2 reactants in there, they're in the same space at the same time, and the solution will just get hot, right? So you can just measure the temperature directly, and that's really a calorimetry experiment, yeah? So it's rare that we kind of bring in heat from the outside. There's a lot of loss to the surroundings there. If we generate the heat kind of in situ, just mix 2 things and then just measure the temperature of the solution as they turn reactants to products, that's much more accurate. And that's what we do from now on. That's kind of the genesis or the basis of your next experiment. Okay. All right, so here are a few exchange rates, so to speak. Okay. So as stated, there's water. Water has the highest of any heat capacity, the highest exchange rate between joules and degrees C change for 1 gram, right? So water has a super high, takes 4 joules to raise 1 gram by 1 degree C. But look at things like gold and silver. They're tiny, 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 which kind of makes sense, right? If you think about metals, yeah, and you have a metal poker and you put it in the fire, it gets hot almost immediately, right? You say, oh, it's a good conductor. Well, good conductors always have low heat capacity. It takes a little bit of energy to make the temperature go up a lot, all right? Okay, so metals generally have low numbers, low exchange rates. A little bit of energy makes the temperature go up a lot. Water in particular, kind of a special chemical actually, it's like the highest, more or less, right? It has the worst exchange rate. You've got to put a lot of energy in to make its temperature go up by 1 degree C. Oh, I feel some extra credit. Extra credit's going to be Tuesday, right? So that's whatever the date is on Tuesday. So Saturday 5th, 6th, 8th. I think Tuesday's the 8th, right? So on Tuesday the 8th, by the end of Tuesday the 8th, have this packet done, and you tell me, can you find anything with a higher heat capacity than water? Is there anything out there with a higher heat capacity than water? I think there's 1 or 2 things out there. Try and be realistic. Don't be giving me like something crazy like, you know, neutron star or something. Something I can find on this planet. All right, okay. Something, you know, people use on this planet that actually has a higher heat capacity than water. 1 point per example. Okay. Now, this math is pretty simple. Okay, we run a few examples just to show you. Okay, if you've done that lab, you've seen the math already. But let's just show you, right? So, just like with PV equals nRT, put the variables in the margin, right? Okay, it's going to be one of those calorimetry problems, right? We can get that by reading it, and then we just put the variables in the margin, right? So, how much heat energy, what's Q, is needed to raise the temperature of 25 grams, 25 grams, of water. This will be on the data sheet. So when it says the identity of the stuff, you can look up its heat capacity. And again, leave units in. Raise the water by 15 degrees C. Now that's interesting. It says raise it by 15. It might have gone 0 to 15, 15 to 30, 30 to 45. We don't know where it started and where it finishes. They'll tell us that in other questions maybe, right? But we just know the change. They just said right off the bat, it changed by 15. So that makes our life a little easier. Okay, so real simple. Q equals Cp times m times delta T. Leave the units in. Heat capacity, mass, change in temperature. Work it out. 1567 joules. Now, 2 sig figs. We always answer in kilojoules, right? So that's, 1.6 kilojoules, right? 1.6 kilojoules. Okay. So it takes 1.6 kilojoules to raise 25 grams of water by 15 degrees C. All right. Now, if you got that one, this next one's going to be simple. Okay. Same exact question, same mass, same change in temperature, but iron has a different heat capacity, right? Can you kind of predict what's going to happen here? Iron has a heat capacity of 0.45, water has a heat capacity of 4, right? So it's approximately 1/10. That tells me I need 1/10 as much energy to do the same thing, right? I need 0.4 of a joule rather than 4 to make it go up by a degree, okay? So I'm going to suggest this will be 10 times smaller, because the only thing that's different is the heat capacity, which is 10 times smaller. So work it out, see what you get. You could put them in the side there. Let's just be, type A here. CP is different, right? 0.45 joules per gram degree C, 25 grams, 15 degrees C. All right. 0.45 joules per gram degree C times 25 grams times 15 degrees C, units cancel, equals 168.8 joules, 0.17 kilojoules. Yeah, it's approximately, oh, move it up, sorry, let's just go through it. So there's your variables, right? Equation. Cp is the smaller number for iron, right? Mass and temperature change are the same. It's in kilojoules a tenth because the heat capacity is a tenth. The exchange rate's much more favorable, if that makes sense. Okay. All right. Now, this next one, try it by yourself. What I did was I tried to get a question like with all the tricks, right? So sometimes because the questions are quite simple, they throw in a few tricks to try and catch you out, all right? Okay, so I found all the tricks, put them in one question. If you can do this one, watch out for the tricks. You'll be okay. All right, so try it, pause, come back. All right. Q, Cp, M, delta T. Careful. How much heat energy, Q is often the thing we want to find, is needed to boil 330 milliliters of water? Wait a minute, that's a volume, not a mass, right? But 330 milliliters and water is 1 gram per 1 milliliter, right? Just so happens it's the same number. If it was a different material, it'd have a different density other than 1. So, you know, you still got to show that, right? 330 milliliters is 330 grams. If it was mercury, it'd be 13.6 times heavier, right, per milliliter. Okay. Cp, that's water again, 4.184 joules per gram degree C. Temperature change, well, that's the only thing we're missing. Now, this is where the trick is, right? So how much heat energy, check, would be needed to boil? Needed to boil. It boils at 100 degrees C. 330 milliliters, i.e. 330 grams of water that's initially at room temperature, 25 degrees C. A few of you put 25 degrees C in your equation, which is wrong. Temperature change is final, it boiled. Minus initial, 25. 75 degrees C. The change was 75. Q, Cp, M, delta T, 4.184 joules per gram degree C times 330 grams times 75 degrees C. What do I get? No, turn over. 1.04 times 10 to the 5 joules, 104 kilojoules. Okay. Now, if you didn't get 104, what I recommend is, rewind the tape a little bit, rewind the video, and just try it, right? And then make sure you get this. Okay. Now, extra credit. Are you a fan of Dungeons and Dragons or Game of Thrones and stuff like that? If the answer is yes, you'll appreciate this one. If you watch those shows, they do lots of stuff with blacksmithing, you know, and you often see when they take a sword and they're kind of like forging a sword, they put it into a big bucket of water and quench it, right? What that does is it hardens the edge of the steel, right? Okay. And you do that to virtually any steel or iron thing to make it less floppy, right? Okay, make it firmer. Okay, do it with horseshoes, right, for example. Okay, so here's the question which kind of pertains to that, yeah? So I'm going to get a horseshoe. There it is, right? And imagine I've got it in my furnace and I'm melting it down. I'd be able to shape it into the correct shape. And now I want to harden it up, right? So I'm going to quench it. I'm going to throw it in a bucket of water. Yeah, okay. So a blacksmith tosses a red hot horseshoe weighing 0.569 kilograms into a bucket of water, 5 liters. All right. The water goes from 10 to 20 degrees C. Okay. Question, what's the original temperature of the horseshoe? Now here's the thing. The horseshoe is going to lose energy, right? It's going to get colder. Where's the energy going to go? It's going to go into the water, right? Until they're the same temperature. So what's lost by the shoe is gained by the water, okay? And of course, Q equals Cp times M times delta T. Be careful with signs. Signs will be a complete pain in the neck in this one. Okay. Think about the heat capacity of iron. Got that on the previous page in the table. The mass of the iron, but in grams, not kilograms. And then temperature change, right? So that's the variable we want to find. We want to find out its temperature change, right? Because it says, hey, what's the original temperature of the horseshoe, right? The final temperature will be 20, right? So we've got to find the initial, because it went, the water went from 10 to 20, the horseshoe went from however many hundred it was down to 20, because they got to the same temperature at the end, right? Then the water, heat capacity we know, mass, well, 5 liters, 5,000 grams. Temperature change, 10, right? It went from 10 to 20, so it's 10. Okay, final minus solution, also plus 10. Careful with signs. If you think about it, the temperature change for the horseshoe will be reversed, if that makes sense, because it cools down. It's going to be negative, right? Okay. All right, so by the end of Tuesday, oh, I'm feeling generous. If you get the right answer, you tell me, red hot horseshoe, how hot is it? Okay, I'll give you 3 points. All right. Show the work, email, you know the stuff. All right. Now, application to chemical systems. I kind of drew you a picture earlier, didn't I? Right. So I showed you what's essentially what we call a coffee cup calorimeter. I think I've got a picture of one over here somewhere. Okay. This is almost exactly how we do it in our lab. Okay, I'll throw this in the. Kind of hard to see, it's a big picture. Okay, so we're mixing some HCl and some NaOH, acid plus base makes salt plus water. That's a very exothermic reaction. Okay, so very simply, you mix the two chemicals together. You could weigh them first if you wish, right? So you got the mass of solutions, right? So weigh them separate. When you combine them, they're the same weight. Okay, and you have a thermometer. You stir it around, measure the temperature change before and afterwards, and then the key thing is when we have dilute solutions, the heat capacity is essentially that of water. Okay, so it's a very simple experiment. You can literally do really good experiments in a coffee cup because the polystyrene coffee cup keeps the heat in long enough so we can measure it, right, as a temperature change. All right, so just apply. Q equals Cp times M times delta T. Delta T from the thermometer, M from weighing the two solutions before, it's going to be the same weight afterwards, and then Cp is just 4.184 because they're dilute solutions, they're essentially water. Okay, so that's our trick. Okay, so recall in your recent lab, oh, we're a little bit ahead of the curve, the lab you're going to do, right, this week, I think. Okay, the change in enthalpy, delta H, for a reaction, okay, is released to the surroundings, right? So those things, the acid and the base, or in your lab, the magnesium and the HCl will bump into each other and react, yeah? And then heat will go into the surrounding water and heat up the water. And then it's just, hey, Cp M delta T, right? Okay, so remember, the enthalpy loss from the reaction comes out as heat into the solution, and you can trap it in that coffee cup, right? You trap the energy in the coffee cup, the solution gets hotter, okay? So Q is measured in joules, okay? As we saw with the previous example, when we do the math, Q comes out in joules, right? But then we typically convert it to kilojoules because it's a nice, easier number to deal with. So we'd rather say 800 kilojoules than 800,000 joules, right? It's more convenient, okay? And remember the big trick, the heat capacity of any solution, because we use dilute solutions, is approximately the same as water, and we just keep it the same. All right, so let's do the math, and this will be very useful for you, that experiment we're gonna do, right? So let's do the math, right? So in this one, we're gonna literally emulate your experiment, right? So 33 milliliters of 1.2 mole HCl is added to 42 milliliters of a solution containing excess NaOH, right? Draw a picture. 42 milliliters excess NaOH. We're throwing in there 33 milliliters of 1.2 moles per liter HCl. All right. We see a temperature change of this, calculate delta H, right? Now, same as before, but now it's a solution, not a brick of iron, right? So, usual thing, Q equals Cp times M times delta T. We'll get Q and then just change the sign and it will be delta H, right? Okay. All right, so Q. CP, well, it didn't say it, but it's definitely implied. It's 2 weak solution, so that's the same as water. Okay, now the mass, we saw that trick earlier, right? 33 milliliters, 42 milliliters, that equals 40, 50, 60, 75 milliliters, right? Oh, it's water essentially, so that's 75 grams, okay? Times delta T, well look, it went from 25 to 31.8. Maybe I'll do the whole math here. 31.8 minus 25, final minus initial, okay. Equals, what do we get? I have to do it on my phone real quick. So 4.184 times 75 times, well that's going to be 6.8. 6.8 equals 2,134 joules, 2 sig figs, 2.1 kilojoules. Hopefully you're at the point now where converting kilojoules to joules and back again is easy, right? Okay, kilojoules. That's for the process itself, right? That's for the process. So we're not done yet, it turns out, because when we define print here, quote your answers is not in just kilojoules, but kilojoules per mole. So we added a certain number of moles of HCl, right, to an excess. So it's limited by how many moles of HCl. So on the side here, I'm going to do a quick calculation. Moles of HCl equals 1.2 moles per liter, that's its strength, times 0.033 liters, right? What is that? 0.0396 moles. All right, so 0.0396 moles of HCl produce that many kilojoules, right? So if I want it on a per mole basis, kilojoules per mole, therefore 2.1 kilojoules over 0.0396 moles will give me the amount per 1 mole, which equals 53.8 kilojoules per mole. Am I done? Not yet, because it wants delta H, which would be minus. Heat came out, Q is plus. Q is the same number as delta H, but delta H is minus. What's lost by one is gained by the other, okay? If you forgot the minus on your answer, it would be a wrong number. You'd lose all points for the answer, so be careful with signs, right? Okay, be careful with signs. Delta H is minus if Q is plus. If Q is plus, heat came out, it got hotter. 99% of the time it's an exothermic reaction, it gets hotter. Okay. All right. So measuring heats of reaction, we just did it, right? We just did it. Okay, so you do your calorimetry experiment, find Q, take Q, change the sign, convert to kilojoules as necessary. All right. To do that, we use a calorimeter. Okay, a calorimeter is simply a device where the reaction happens, where you can measure the heat change, right? It can be as simple as a coffee cup calorimeter like this. Okay, I've got a couple of pictures in the back here. If you look in the back of your packet, here they are. Okay, so you can get some really, really good answers by using a coffee cup calorimeter. Yeah, so polystyrene cup, super insulating polystyrene, right? So use a polystyrene cup. It keeps that heat in long enough to measure it, yeah? Okay. If you want to be super hardcore, 2 polystyrene cups. That's the mark of a true chemist. Right? That really cuts down on heat losses. Cork lid again, to prevent heat loss. We need to measure the temperature change so that thermometer sits in the solution. Important, has to sit in the solution, not touching the bottom, right? And then we stir it around to prevent hot spots, right? So you throw your chemicals in, shut the lid, record the initial temperature, then record the final while stirring. Final temperature, initial temperature. You can, what I typically tell my students is, you know, weigh the empty container. Then when you finish, take it over to the balance, weigh it again, subtract for the mass of the solution. CP is just that of water. Okay, so a coffee cup calorimeter works really well. You'll be using something like that in lab, should we have been in lab, but I guess we're going to do a virtual lab with this, right? in the real world, if you ever wonder how do they know that, you know, peanuts contain 75 kilojoules per gram or whatever, right, whatever the number is, okay, they use a bomb calorimeter. A bomb calorimeter is just something that's more accurate, right? So what we do is we have basically a sealed container, hence it looks like a bomb, right? Okay, and in this big kind of drum we have a bunch of water, yeah, and then connected to it is this internal container which has a high pressure of oxygen inside it, yeah, and the sample we're going to kind of combust. It's always combustion, right? And then you know, some sparker here, right? So what happens is the heat capacity of this whole thing, right? So bomb calorimeters, when you buy one, okay, on the first page of the manual, the whole page tells you CP for this, well, C for this device. It's not CP because it's not standardized to 1 gram. Anything has a heat capacity. I have a heat capacity, so do you. It's, hey, how many joules does it take to make you go up by a degree, right? Not per gram, but per thing, all right? So this object has its own heat capacity, right? How many joules does it make for this object to go up by 1 degree C? Okay, so that simplifies our equation. There's no mass now because it's per device, right? Every bomb calorimeter is determines C to many, many decimal places, okay? So this whole thing will get hot. Its heat capacity is here, and we just look at the change in temperature of the whole thing, okay? And it kind of happens here, and then the heat spreads out through the whole thing, okay? So we have the same features. We have a stirrer, we have a temperature measurement. It's just a different way of getting the heat into solution, okay? Just a different way. The high pressure of oxygen makes sure it all burns very well, and the sparker just makes sure it starts on fire, okay? So that's a bomb calorimeter. All right, so there they are, okay? So a bomb calorimeter, used, you know, by food companies to find out how much energy is in your food. Experimental, right? So it's not something they kind of work out. If you look at food labels, it's something they actually do. So they might put a Snickers bar in there. That's a good job, right? Burning Snickers. But that's how they do it, okay? In the lab, coffee cup calorimeter. Very good results from that. Not quite as good, but very good. Okay. Now, as you mentioned, for a bomb calorimeter, because it's the device itself that has a heat capacity of the calorimeter, the equation is much simpler. You would never use that because we just use solutions in a cup. We'd use the mass and the heat capacity of the solution, right? 4.184, because it's dilute. Okay. All right, that's where I want to stop. This will be the end of part 1. I'll throw out part 2 in a day or so. Okay, but in part 2 we're going to get on to theoretical treatment, right? So once we've got our numbers for delta H, so we do our experiment with calorimetry, we get Q, we change the sign, put it in kilojoules per mole perhaps, right? And we get our delta H number, okay? Now delta H is interesting because it's what we call a state function, okay? And there's some interesting math that accompanies state functions. If I'm going to kind of just summarize that in one sentence, it doesn't matter the journey you take, it always costs the same. Okay, so we'll see that come into action when we talk about it. Okay, stop there and talk to you guys next time.